Welcome back. So the week 5 lectures will be on the so-called first method of Lyapunov, or Lyapunov's indirect method, which depends on something that we are really familiar with, that is how to analyze linear systems. Using the knowledge of linear systems, we will graduate to nonlinear systems in terms of how to use it. As the name suggests, actually it's Lyapunov's first method, or the indirect method is now called. What we have seen in last week, it's the so-called Lyapunov second method, or direct method. Direct methods are far more useful when it comes to certain essential nonlinear systems, but indirect methods are far more useful because most of the systems can be linearized, and one can actually talk about stability through linearization, right? So it's perhaps some of you have already seen a detailed study of linear systems, but I would like to go through a summary of that in these next couple of lectures, and then show the summary of first method, and then of course show some examples, and then move forward from there. So let me demonstrate this. As usual, we will start with something very simple and my favorite, x dot equals ax, which is a scalar, right? So by now I don't have to keep on showing why this is the case, but the solution for this particular system is e raised to at times x0, right? So essentially, whatever the value of x0, if x0 is 0, then of course x of t is going to be identically 0, right? So that's the equilibrium point. Anywhere else, the function that is going to determine what's going to happen to this system is basically e raised to at, right? Now let's see what we know about e raised to at, right? So if a is positive, then e raised to at goes unbounded. Okay, it's 1 consistently if a is equal to 0, and goes to 0 if a is less than 0. Okay, so if we want asymptotic stability, clearly we want a less than 0 for asymptotic stability. Okay, and clearly if a greater than 0, then that's unstable, because the definition of Lyapunov stability is even closest to the 0. We should not be able to find anything that is going to go off. Conversely, basically we should be bounded within small region of that 0, right? Of course, be careful, a less than 0, I said asymptotic stability, but in reality I should have said convergence first. Okay, I mean it is correct in terms of asymptotic stability, but for the time being I'm going to say a less than 0 gives convergence, right? So what about the only remaining case is basically a equals 0, and that simply says if a is equal to 0, then wherever we start we remain there. Okay, now is this Lyapunov stable? Well, let's look at it. Let's say this is the origin. If I'm going to start very close, I'm going to remain there. So that means the bounded condition of Lyapunov stability is satisfied, right? So therefore a equals 0 certainly implies, a is equal to 0 implies Lyapunov stability. Okay. And furthermore, if a is less than 0, if you are starting somewhere, it's not going to go wander off, it will just directly go to 0. Okay, it will have Lyapunov stability, so it remains bounded close to the equilibrium, and convergence, right? So that gives us asymptotic stability. Okay, so what does this mean? Just three cases. A, if it is greater than 0, we get unstable equilibrium. Is equal to 0, Lyapunov stability, or I'm going to say less than or equal to 0, Lyapunov stability. And strictly less than 0, asymptotic stability. And there's nothing more complicated than this, right? Okay. So scalar systems are a nice way of entering anything more complicated. Scalar linear systems, for that matter, are the first steps to anything complicated, right? So, but then scalar systems tends to be quite simplistic, and then this is what we find. Okay. The next best thing that one can do is basically, let's say x dot equals ax, where A is actually a diagonal system, right? I'm going to say A1, A2, and so on and so forth. Okay. Now, the nice thing about this particular system is basically, in other words, you'll have x1 dot equals A1 times x1, x2 dot equals A2, x2, and so on and so forth. So we have n independent systems, okay, scalar systems, okay. So therefore, if we treat this, so if we have this x dot equals ax, where a is diagonal, we'll have n independent scalar systems, and therefore we can conclude the same thing that we just concluded. If a1 is less than 0, then we'll have asymptotic stability. If a1 is less than or equal to 0, then we'll have Lyapunov stability, and if a1 is greater than 0, we'll have instability. So of course, when we have a coupled system, if one of the scalars is going to be unbounded, then we call that unstable. All of them have to have less than or equal to 0 for Lyapunov stability, and then all of them have to have less than 0 for asymptotic stability, right? So it's very simple. I'm going to use this notation. 0 implies Lyapunov stability. Okay, so this essentially says A has to be less than or equal to 0 in every element, whereas for asymptotic stability, we need all the diagonal elements to have strictly less than 0. Okay. Now, but how good is this system where we have all diagonal elements, right? Well, let's go back a little bit and then understand matrices, so to speak, square matrices and eigenvalues and things like that. If you recall, basically, the definition of eigenvalue is something like this: ax is going to be equal to lambda x, where x is non-zero and lambda could be 0. So lambda, and typically we cannot always get real numbers. So basically, we assume when we talk about eigenvalues and eigenvectors, we typically extend the space to complex spaces. So any x, non-zero x that satisfies this becomes an eigenvector, and then the corresponding value lambda is called eigenvalue, right? And suppose a is n by n, then we actually have something like n such equations. One simple thing that one can do is basically we can put all of them in next to each other in a column fashion, and we will be able to write this as matrix product of these matrices, right? So all the eigenvectors put together next to each other, let's call that S, and you'll have the same thing on that right hand side as well. And all the eigenvalues, the way these things are, we can easily see. Yeah, we can easily see that we can write this this set of equations as basically a simple matrix equation as A times S is equal to S times T, right? This is a nice thing to remember. Um, you know, uh, uh, n by n matrix is guaranteed to have n eigenvalues and n eigenvectors, so we can always do this, right? What is not guaranteed is basically the character of S. But suppose if we are lucky enough that if a determinant of S is non-zero, that means S inverse exists, okay? So then we can basically say that A equals S d S inverse, okay? Such matrices are called diagonalizable matrices, okay? So if you have a diagonalized matrix, basically you can always write it as S d S inverse, and then there are large classes of matrices where this can be guaranteed. Symmetric matrices, for example, and matrices that have all distinct eigenvalues and so on and so forth. There are a bunch of classes. Okay. So what does this fetch us? Well, let's say we have some system where x dot equals ax, where a is diagonalizable. Okay, so that means SDS inverse. Let's write this as y equals sx. Okay, so then what we will get is y dot is equal to sx dot. Okay, sorry, S inverse x. So let's define y equals S inverse x, and then y dot is going to be S inverse x dot, which is S inverse ax, which of course is equal to S inverse S d S inverse x. Of course, S inverse is x, S inverse S inverse cancels with each other. We eventually get d times y. So we will get d times y as our system. But d is bunch of independent systems because d is diagonal, right? Except the only difference that we have considered so far, the d could be complex. Okay. The nice thing about this system is we can say something like this. If the real part of d is greater than for any I, for any of this thing, then we have instability. Okay, and if real part of d is strictly less than for all I, then we get asymptotic stability. Okay. If real part of d is equal to 0 for all less than or equal to 0 for all I, okay, then we get Lyapunov stability. Now, if we know something about y, can we conclude therefore same thing is true about x? Well, remember y is S inverse x, so that, and there is famous inequality of norms of such vectors and matrices. We can show that y less than or equal to some kind of norm of S times norm of x. Okay, which also can be shown some other number times y. So I'll leave this as a homework for you to figure out what should be, how do we do an upper bound in terms of between this and that, right? So eventually we can basically conclude that x is going to be upper and lower bounded by some alpha times y and beta times y. Okay, and then like I said, alpha and beta are left as homework in terms of what they are, right? So what is nice thing about this is basically if somehow we know that y is going to 0, x is going to go to 0, right? If y is bounded by some epsilon, x is going to be bounded by epsilon, both upper and lower, right? So in fact, there's a famous fact that says all yeah, forget about that. I was going to say something about norms being equivalent, but that's not relevant here. That's relevant if somebody asks the question, basically, should we always use the Euclidean norm? And then the answer is no, we can use different norms and then we get similar logic. But here, basically, this y equals S inverse X is called a similarity transformation. And and any such similarity transformation, if you have two systems that are connected through a similarity transformation like here, we can conclude if one system is stable, one zero equilibrium is stable, then the other zero equilibrium is stable. And of course, this particular similarity transformation is very special. It is coming from the set of eigenvectors inverted and things like that, right? So, so therefore, one more thing. I mean, if we have something like A equals SD S inverse, D are the eigenvalues of A. So therefore, we can directly conclude about A in terms of its stability, where A is diagonalizable. Okay. So then what can we say? Real part of eigenvalue of A, okay, any of them for positive for some I, implies instability, right? Any one of them is going out to infinity, then basically any of the eigenvalues, then we can conclude instability. But concluding asymptotic stability, we need strictly less than 0, the real part is less than 0 for asymptotic stability. And if it is less than or equal to 0 for all I, then we have Lyapunov stability. Okay, so that's kind of the summary of what we have been doing. If we have a diagonalizable matrix A, then things are quite straightforward by just looking at the eigenvalues, and that too specifically real parts of eigenvalues. So what are the imaginary part of the eigenvalues doing? Well, we will hopefully see that somewhere later, right? So what about non-diagonalizable matrices? Well, let's start with an example. As always, if we have something like A equals 0, 1, 0, 0, okay, um, no matter what we try, and I'll show you, what are the eigenvalues in this particular case. I can let you think about it. Basically, both eigenvalues are 0 and 0. Okay, I'm writing 0 and 0 to emphasize that we have two eigenvalues at the same point, and that's always possible, right? And let's try to do this. Try to find what are the various values of x, right? So such that this satisfies for lambda equals 0. So we will have 0, 1, 0, 0 times sum x1, x2 is equal to 0 times x1, x2. So this tells me x2 is equal to 0, right? Whether we put the first 0 or the second 0, we get the same equation, so x2 equals 0. So the only x vector is basically something like 1, 0 or 2, 0, or in general some, a comma 0, right? So unfortunately, how many ever we take such vectors, you put them next to each other, S therefore is going to be something like, let's say 1, 0, 2, 0, okay? If you take S to be this, then basically AS is simply 0, 1, 0, 0 times 1, 0, 2, 0, and we will get S times D, where D is 0, 0, okay? I mean D is a 0, 0 matrix. And you can see basically this times this is 0, this times this is 0, everything will become 0. So we still have AS equals SD, except S is given by this, and then there is no other possibility of S satisfying this, and S is not invertible. Specifically, determinant of S is 0. So that's a problem. So this is one of those systems where it is not diagonalizable. Now let's try to analyze this. So you have this x1 dot is equal to x2, and x2 dot is equal to 0. So unless x2 of 0 is 0, okay, we will have a problem. What kind of problem? We'll see in a second. Suppose x2 0 is 1. Of course, that means x2 of t is 1 because x2 dot is 0 in this particular case. So x1 dot therefore is 1. Okay. Whatever the initial condition may be, x1 therefore is basically going to be x1 0 plus integral 0 to t dt, and that's equals x1 0 plus t, which is going to go off to infinity as t tends to infinity, right? So this is a serious problem in the sense that if we have this particular system, then basically we'll end up with instability, right? So if we have non-diagonalizable systems, then we can have the possibility of unboundedness. Okay, but let's take a slightly different example, something like -1, 1, 0, -1. Homework for you is show that A is non-diagonalizable. Okay, yeah, I mean I just showed how to do that for one example, and you can try showing this. Now, how do I try to reconcile this particular system? Again, we'll have something like x1 dot is equal to minus x1 plus x2, and then x2 dot is equal to minus x2, right? So this implies x2 of t is some e raised to minus t, some constant, and x1 dot after manipulation you will get something like basically x1 of t is going to be equal to e raised to minus t and then times some integral, right? The only question is whether that integral is going to be bounded or not compared to this, and then whether this is going to go to 0 or not. So but for now I will give you an intuitive reasoning why I think that this is not a problem, is something like this, right? At some point this x2 is going to be very small, right? If x1 dot is going to be small enough, that may take this away, but this is continuously getting smaller and smaller. At some point this is almost equal to 0, and if this is x1 is far off from origin, this particular part is not going to play part, and x1 is going to take you to close to the origin. x2 is already very close to 0, continue to reduce to 0, and x1 therefore will continue to go to 0, right? If x1 is already close to 0, one has to convince ourselves that this is going to be unbounded, but this is going to be continuously decreasing, so that's a nice thing. So in this particular case, I didn't prove it rigorously, but x1, x2 both go to 0 as t tends to infinity, right? So that means we have asymptotic stability, right? Or at least convergence, and then we can convince ourselves that this is asymptotic stability. We also have Lyapunov stability. Okay. Now this is one of those non-diagonalizable systems where we have asymptotic stability, right? So what are we talking about therefore, right? And in fact I can convince you, even if this is a complex system where we have a similar condition where the real part is less than 0, we can conclude the same thing, right? The only problem we get for non-diagonalizable systems is when we have real part 0, right? So that is what we can for now summarize, and then I'll show you a slightly different way of looking at it. If we have non-diagonalizable A, again a real part of eigenvalue of A less than 0 implies, and we can do this, but anyway, asymptotic stability. Okay, but if real part of eigenvalue of A equals 0, question mark, right? As you can see, basically in certain cases, in diagonalizable cases, we can have Lyapunov stability, and in the case of non-diagonalizable matrices of certain features, then basically we'll end up with unboundedness, right? So all this boils down to the following: if A is equal to SDS inverse, easy. And then we use this similarity transformation and things like that. But what about systems that may have some features that we just saw in terms of non-diagonalizability? Well, nice thing about this is basically there's something called Jordan decomposition, my favorite decomposition when it comes to matrices. And it looks identical to your diagonalizable decomposition, except J is not diagonal, but it's actually block diagonal. It will look something like this. Okay, so otherwise it's the same thing, except S need not be eigenvectors, right? In some cases it can be, but it's not always necessary. But what is Ji? So Ji is going to be the usual eigenvalue times identity. So the all repeated eigenvalues could go into that particular matrix, or some of the repeated eigenvalues, plus something called Ni, where Ni is a nilpotent matrix. Okay. What is a nilpotent matrix? Nilpotent matrix is something that when we take this and then multiply with some number, at some number it's going to go to 0, right? After that, of course, any times you multiply, it will remain 0, right? Any such matrix is called nilpotent matrix. One of the simplest and most beautiful or villainous nilpotent matrix is what we just considered earlier. This is a nilpotent matrix. Clearly Ni square, 0 1 0 0 times 0 1 0 0 is 0 0 0 0, right? So of course, if you have Ni is equal to 0, that's also nilpotent, right? I mean, Ni power 1 is 0. So Ji can be lambda I plus Ni, where Ni is nilpotent, including 0, right? So if all Ni's are 0, then A is diagonalizable, right? I mean, therefore, this Jordan decomposition is sort of an extension of diagonalizability, but not so much because it's far more complicated than diagonalizable. S is not eigenvectors and so on and so forth. But if Sj is inverse, where J happens to be just the diagonal part, then we get back to the diagonalizable and S becomes the set of eigenvectors and so on and so forth. But in most cases, basically, Ni could be non-zero, and every time Ni is non-zero, we get unboundedness. Okay. We'll see that in a few minutes. But essentially, it boils down to whether a particular block has this form, right? You can have Ni 0 or not. But if Ni is not 0, the only thing that can save you is basically real part of lambda I has to be less than 0 if Ni is non-zero. Then we'll have convergence, right? So the problem Jordan matrix is the following. Is when real part of lambda I is 0 along with ni non-zero. Okay, everything else is fine. Everything else is going to be bounded. If real part of lambda I is less than 0, then we'll have convergence. If real part of 0 is 0 and then ni is 0, then we'll have kind of boundedness that corresponds to this Lyapunov stability kind of condition. But if we have this condition where Lear part is 0 but ni is non-zero, then that's a problem. And of course the usual stuff where real part of lambda is positive for some block, then that's also unbounded, right? These two are unbounded cases. And the nice thing about understanding this is basically the Jordan form gives you that, right?